Swayam Prabha. Digital India. Educated India.
So last class I have discussed that how you will get the response under different conditions to example problems. Now today I will discuss how I will use the proposed attenuation relationship or the predictive relationship to get the our ground motion parameters by using two different examples. So before I go to those part to apply those equations in numerical or example problems, I should give you some idea about seismic hazard analysis. Though this is not the part of this course, because the seismic hazard analysis is not part of this course. It is not in this course content, but still I will give a brief idea what is seismic hazard analysis and how I will use those proposed attenuation relationship that I discussed in previous lectures to get the seismic ground motion parameters. Now, the seismic hazard analysis is the quantitative estimation of ground shaking hazard at a particular site. So, it will give me the quantitative estimation of ground shaking hazard at a particular site. So, to do that, the first and the major important task is to identification of earthquake source, because I have to identify the earthquake source. A different way I can identify the earthquake source, that the geological evidence, tectonic evidence, historical seismicity, instrumental seismicity. So we will get from there. I will get that seismic source for a particular location. Suppose I want to do the seismic hazard analysis of a particular site, and where I will use those attenuation relationship, but here it is mentioned that is the distance of from that site to nearest fault. So that means there may be a n number of source on that particular site or around that site. So I have to identify all the source. Then for each source, that expression they have to apply. Okay, it's not that there will be only one source. So that means first is the identification of the earthquake source. I am not discussing in detail so in these things, but the main aim of this particular lecture is to show you how I can apply those attenuation relationship to determine the ground motion parameters or to estimate the ground motion parameters. Okay, to do that, what are the things are required, that I will only discuss. Okay, in brief. So that means we identify the sources. Now here the seismic hazard analysis are two types. One is the deterministic seismic hazard analysis, another is the probabilistic seismic hazard analysis. Now deterministic seismic hazard analysis, what is deterministic seismic hazard analysis? The strong ground motion parameters are estimated for the maximum credible earthquake or the controlling earthquake assuming to occur at the closest distance from the site of interest. So, for deterministic seismic hazard analysis, strong ground parameters are estimated that for a controlling earthquake, that means first we have to identify a controlling earthquake, and that will possibly assume to occur the closest distance from the site of interest. Later I will show one example problem. So, then what are the steps? That identification and characterization of all possible earthquake sources, those are capable to produce earthquake. Then first you have to identify the possible sources near your site of interest, those are capable to produce earthquake. Okay. Next is the selection of source to site distance. Distance parameter for each zone of source. That means if you identify the source, then your selection of source to site distance, that R value, source to site distance, distance parameter for each source node. For each source, you identify the source to site distance. Then select the controlling earthquake. What will be the controlling earthquake? Then the hazard at that site is defined in terms of ground motion produced by controlling earthquake. Then that controlling earthquake you choose, then only that single earthquake you will consider to determine my ground motion parameters, or the hazards are defined in terms of ground motion parameter produce that particular earthquake only. But there is a issue that we are not sure that whether that earthquake will come or not in the entire design period of a particular structure. Okay, but you have to taking the maximum one. But in case of probabilistic seismic hazard analysis, it incorporates the effect of possible earthquake of any size at any point in each source during a particular time period with the associated uncertainty taken into account. That means here we will take care those probability that whether that earthquake will occur or not. But remember that in the deterministic seismic hazard analysis, we are taking only the controlling earthquake. But here, each possible earthquake at any size, at any point on each source, we will consider. Okay. So that means here steps are identification and characterization of all possible earthquake sources. Those are capable to produce earthquakes, like the deterministic seismic hazard analysis. In addition to, we will some probability rule we will apply. Okay, and I am not discussing those probability concept here in this class. I will just discussing these things to solve or to show you how we can use those ground motion estimation relationships. Now, once we do that, then characterization of seismicity for each source. We will characterize the seismicity of each source. Then determination of ground motion at the site produced by earthquakes of any size at any point in each source during the using the predictive relationship. That means we will use the predictive relationship not only for the controlling earthquake, but the all earthquake at any size at any point within the source. Okay, and then uncertainty in earthquake location, size and ground motion parameter prediction are combined or will be combined, and probability of the ground motion parameters to exceed that value during a particular time period will be computed. That means we will combine these uncertainties of that earthquake location, size and ground motion parameter prediction, and then probability of ground motion parameter that to exceed that value during a particular time period will also be computed. Now let's discuss about the example. I will discuss one example for deterministic seismic hazard analysis and one example probabilistic seismic hazard analysis. So let's discuss this. Okay. So now we have a site. This is our site, or this is our site of interest whose coordinate is taking 0, 0. This is our site, and this site 3 possible sources or earthquake sources are being identified. Okay, what are those sources? This first source, this is our source number 1. Source number 1, which is a point source. It is a point source. Okay, whose coordinate is minus 50, 0. That means it is 50 kilometer away from the site. So this all are in kilometer. This minus 50 means it is 50 kilometer. Second source is your, this is my source 2, which is a area source. Area source whose coordinates are, this is minus 10 kilometer, this is 30 kilometer, this is minus 50, this is 30, this is minus 10, this is 80, and this is minus 50, this is 80. These are probable sources. And then third source, it is a line source. Source 3, it is a line source, okay, whose coordinates are plus 25 kilometer to minus 40 kilometer, and this is 70 kilometer and 80 kilometer. So first to identify these sources with respect to the site, what are their coordinates, that we will identify, and now we identify what is the maximum possible earthquake, the size of earthquake this source can produce. Okay, so here the M max, maximum possible earthquake, it can produce with a magnitude of 7.1. It is a magnitude I am talking about, is a moment magnitude. So it is a maximum possible earthquake this source 2 can produce is a moment magnitude of 7.1. Source 1, it is M max is 6, and source 3, M max is say 7.6. So these are all the information we have. Now what I will do, that for these things I will make a table. Source, this is distance. Distance means we are talking about closest distance, okay. Then MW, then PHA, okay, and we can use the PHV also, okay. Now first source, the distance, closest distance will be 50, that is the closest distance, so 50 kilometer. MW is 6. PHA I will calculate, PHV, PHA I will calculate. Now for source 2, what is the closest distance? This will be the closest distance. It is this area source, this will be the closest distance. How I will get this closest distance? This will be 30 square plus 10 square. So this will be 31.6. Now MW is 7.1. And third one, I know the coordinate. So what I have to do, I have to draw all these coordinates in a proper scale, and then draw this your line source, and draw a perpendicular line from the side to the source for this line source, and that will give me the closest distance. And then you measure that perpendicular distance, closest distance, then convert it to the real value. This is in scale drawing. So now you convert it to real value, and that value I have determined, that is coming out to be 37.34 kilometer, and its possible earthquake is 7.6. Now here if you see that deterministic seismic hazard analysis, it is assumed that is a controlling earthquake at closest distance from the site of interest. So okay, so among these, what is the closest distance is 31.6. So possibility that 31.6 is the closest source of earthquake from the site. But if you see, the maximum magnitude can produce is 37.34. So that is also very close to 31. So what I will do, but here this is 7.1, here 7.6. So now to identify the controlling earthquake, directly here just to the closest distance that controlling earthquake, whether it will work or not, because here the distance at 2 and 3 are more or less same, but distance 2 is closer that distance, the distance of source 2 is closer than the distance of source 3, but the distance at the source 3, the maximum earthquake size or the earthquake size is higher than the earthquake size at source 2. So let's do that. That now the question is, I have discussed so many attenuation relations. Which one I will use? Because I use the simple one just to explain you. Actual real case, you will get the more complex one, get the more value. Because the problem is that here I don't have any all the information I don't have. I have only the M value and I have only the R value. Because I have given the your relationships where the fault characteristics are required, where the your soil type is required, so many things are required, and in the advanced modeler so many things are required. So those, because the actual case you have to gather those informations and then those equations, because you should use the most advanced relationship. Because this 1981 or 1994 relations, these are old relationships, only simple relationships. But you should use the more advanced relationship, and for that you need to gather more information. Then you will get the better prediction. But here I am just explaining you how to use this relationship. That's why I have taken a very simple problem. Okay, and I have taken only the M and R. Clear? So that's why now we have the Cornell expression. Cornell expression I can use because I have here it is only M by R. Now Campbell 1981 expression also I can use, because in that case it is moment magnitude is given in the example, but I have to convert it to local magnitude and the surface wave magnitude depending upon the magnitude. So then here I can use this chart. I have already discussed that. Here you can see that this chart, if I have the moment magnitude, from there I can get the local magnitude ML and I can get the MS also from this chart. Here you know that here some saturation issue is there, so that's why the local magnitude or the surface wave magnitude or the body wave magnitude we cannot use for all the cases. They have some limitation, but the moment magnitude, this is the only magnitude where no saturation takes place, so that we can use it for all the cases and specifically for larger size of earthquake. So that as I discussed that the your surface wave magnitude saturation value is around 8, so we cannot use beyond, if the magnitude is beyond 8, so that is not the correct value. So we cannot use that magnitude scale beyond earthquake of magnitude 8 for surface wave magnitude. Similarly, for body wave magnitude, it is 6, around 6. For local magnitude or Richter local magnitude, it is around 7. Actually, the body wave magnitude scale and Richter magnitude, it is in between 6 to 7, you can say. So for it is saturation start around 6, this is 6, and for local magnitude scale it is start around 7, less than 7. So it is in between 6 to 7. Okay. So that's why these are the limitations. I have already discussed where the saturation starts. So beyond that, we cannot use those scales. So now you can convert it and you can use this magnitude scale also. But here I will use the Campbell magnitude scale. So and I will use, if I use the Campbell magnitude scale, and then for the site 1, for my site 1, if I use the Cornell magnitude scale, okay, if I use the Cornell et al magnitude, this attenuation relationship, and then for the if I use the Cornell et al, then I will show you only one particular site, and rest of the site I will give you the value only. So first case, your site or for source 1, it is ln PHA, it is in gal. So that is 6.74 plus 0.859 into M. You can see into M, and that is R. So M is first source is 6 and this is 1.80, ln R is given 50, then plus 25. Now if you solve it, you will get 0.062 G, considering 1 gals is equal to 10 to the power minus 3 G, or you can take 1 gal as 1 by 981 G. Okay. So 10 to from there. So now for source 3, 2, so this will be ln PHA. So this will be actually PHA. PHA is this value, peak horizontal acceleration. PHA into gal, so that will be 6.74 plus 0.859. So magnitude is 7.1 minus 1.80 ln, this is 31.6 plus 25. So this will be equal to 0.264 G. Similarly, so that means here it is 0.062 G, this is 0.264 G, and for source 3, similar way you can calculate, it is coming out to be 0.34 G. So in terms of PHA, the source 3 or this earthquake, source 3 with magnitude 7.6 is my controlling earthquake. Okay, you can see it is maximum, it is giving maximum. Now for the, I cannot use the Campbell's 1990 Campbell's 1994 relationship, because we have soil types, rock types, and the fault characteristics are required. Those information I don't have. Okay. Now to calculate PHV, I can use this expression. So I can show you how I can use these expressions. Just for location 1, I can show you. So for the location 1 or source 1, I should say source 1. Source 1, it is log PHV. So I can write this value is log, this is base 10 PHV, it is in centimeter per second. So J1, if I take the larger one, say I am taking the larger one. So J1 will be larger one, 2.17 plus J2 is 0.59, 0.49, then MW is 6 minus 6, MW is 6 for source 1, plus J3 is 0, plus J4, it is minus 1, and MW is 6 minus 6 whole square, that is also, J3 is 0, J4, so your J3 is 0, J4 minus 1 into log 10, R is 50, okay. So because R is 50, so now R is 50 will slightly change, because R is actually your R0 square plus J7 square. So here R0 is 50 square, J7 is 4 square. So it will be around 50.16 kilometers, slightly increase. So this will be 50.16. 50.16 plus J5 is minus 0.0026 into R, that will be 50.16. J6 is plus 0.17. Clear? Okay, so this is 2.17 because I have taken the larger one. J2 is 0.49, 6 minus 6, J3 is 0, so that is gone, and J4 is minus 1 into log R, we can calculate by here like this, and then J5 is minus 0.0026 into 50.16 plus 0.7. So it will be the PHV, that value is coming out to be 3.23 centimeter per second. Similarly, for source 2 also you can use this technique, you could use this relationship, but remember that in that case it will be 7.1 minus 6 or 7.8 minus 6, because that moment magnitude value will change, because source 1 it is 6, it is different. So now if I put these values, finally I will get the, if I put this value, this PHV, it is in terms of centimeter per second. So this will be 3.23, then this is 19.64, and this is 28.3. So from this PHV consideration also, this source 3, this earthquake is the controlling earthquake. So now I can get the controlling earthquake. So rest of the parameters I will determine based on these earthquake only, as I discussed in my previous lecture. So other parameters also you can discuss. So that means during design these will be our controlling parameters. So that, so PHA will be 0.34 G and PHV will be 28.3 centimeter per second. So that only the controlling earthquake we will consider, and that is in this case is the source 3. Okay. So this is my, this way I can use those attenuation relationships. Now let's discuss it for one particular case, for the example of probabilistic seismic hazard analysis. So here it is given that determine the probability that an earthquake of moment magnitude 7.5 can cause a peak horizontal acceleration greater than 0.15 G. What is the probability that an earthquake of moment magnitude can cause a peak horizontal acceleration greater than 0.15 G? Site is in hard rock with normal fault, and closest distance from the site to fault is 20 kilometers. So here it is given, the soil type or rock type is given, and then fault nature is given. So I can use these Campbell and Bojorgnia 1994 relationships also. So let's do that. So I will get, this is my ln PHA gal. So that will be equal to, what is the equation? So this is the equation. Okay. So here, so let's put these values here, that will be easier to understand. ln PHA gals, this will be 3.512 plus 0.904, and the MW is 7.5 is given, 7.5 is given, minus 1.328, and this is ln, then root over. Okay. So R is 20 kilometer is given, R value is given 20 kilometer. Okay. Then plus 0.149 exponential, that is 0.647 into 7.5, that is square within root. Then plus what would be your f value? What is it? You see, the f is equal to 0 for strike slip and normal fault. So here which type of fault is given? It is a normal fault. Okay, so f will be 0. So this part is 0. Then your SR, what is SR value here and HR value here? It is given hard rock. So that means soft rock, this will be also 0. So this will be also 0 because your, in case of hard rock, SR is 0. So SHR will be 1. So SHR will be 1. So that will be 0.405 minus 0.222 ln 20, and this will be into 1. So from here I will get that this is 5.624. Remember this ln PHA gals is 5.624. So now what is standard deviation here? ln PHA standard deviation, it is 7.5. So it is greater than 7.4. So this value is 0.38. This value is 0.38. Okay. Now from here, this is ln PHA is this value 0.38, or what I will do, I can convert this from here. I can write PHA in gal, that will be 277. So it is ln PHA gal is 5.624. I am taking PHA gal is 277. Now up to this it is I will get from here. So now here I will use the standard deviation part also. Now how I will solve the rest of the thing? So here, given there is a probability of an earthquake of moment magnitude 7.5 can cause a peak horizontal acceleration greater than 0.15 g. So it is a probability concept you have to use. So here I am calculating the standard normal variate. Z value, I will calculate that. That will be ln PHA minus ln PHA bar divided by that now standard deviation ln PHA. Because that is a standard probability concept, and then you can see these things because I am not discussing in detail, because that part only a small thing, and this standard normal variate I can calculate here. So this is my ln PHA will be what? Now here ln PHA will be this value and ln PHA bar will be this one. So now this is ln PH bar, this is bar. Okay. So now if I put that, now this is my ln PHA. So it is given in terms of G. So if I take, this is 981. So that will be also in gals. Okay. And then this is ln. In terms of gal, it is 277 gal. Because I have already got this 277. And it is given in terms of 0.15 G. So that I have converted to gal. Now here it is 0.38. I have already calculated. So this value will be minus 1.66. minus, so this standard normal variate will be 1.66. Now the value of CDF of the standard normal distribution so we are taking a normal distribution, that is the most common distribution for this earthquake problems. So we will get that this table is available, standard table is available, from there you will get this value. So my Fz, that is now 1.66. Okay, so the probability of that Z less than 1.66, that means the probability of A max minus 0.15 less than 0.15 G, that is will be that value 0.0487, that I will get from the table. This is from the table, the standard table which is available. I am not giving this table is available. So from there I will get this value. Okay. So now here it is given the probability of A max, because it is minus 1.66. So probability of Z less than 1.66 is probability of A max less than 0.15 G. But here it is probability greater than 15 G. So this is less than is this one. So I can write that PHA or A max greater than 0.15 G, that will be equal to 1 minus this value 0.0487. So that will be equal to 0.9513. So here you can see what is the Z value. I can see Z is x minus x bar divided by sigma. So what is x? X is the normal random variable, which is here 0.15 G. Okay, and x by is the mean of x, which is the mean value, the expressions, those are given, the attenuation relationships, and sigma is the standard deviation of x. Okay, so that means that this is the probability of that horizontal acceleration greater than 0.15 G is 0.9513, and it is less than 0.15 G, obviously it will be 0.04487. So this way we can use the attenuation or the predictive relationship, those are given. So I have solved two problems. One is for just to show you what is the difference between the deterministic seismic hazard analysis and probabilistic seismic hazard analysis. So that for a particular site you have to first select those earthquakes, and then you can use these attenuation relationships, and then you can get what will be your controlling earthquake in case of deterministic seismic hazard analysis, and then you will get the probability here, whether that for a particular earthquake of magnitude this, whether what is the probability of acceleration greater than 0.15 G by using this attenuation or predictive relationships that I have shown. But that probability seismic hazard analysis is not only this only one case that I have discussed. It is not like that. I have only discussed that how to use this attenuation relationship. There are so many other models are there, methods are there. So those are not discussed here, because those are beyond the scope of this course. Okay, because here I have given a very brief idea just to show you how we can use those relationships or the proposed relationship or the proposed attenuation relationship to determine the ground motion parameters. So, in the next class I will start my third module. This is the end of module 2. This is the end of module ground motion, seismic ground motion. That module is end here, or you should say the strong ground motion. But then the next class I will start my third module. What is that will be the estimation or the measurement of dynamic soil properties by using field test and the laboratory test. So first next class I will discuss about the field test, and that will continue for few lectures. Then I will discuss about the laboratory test also. Thank you.